Oh, yeah, here we go into, well, basically a launch into all of our series convergence and divergence tests. So for the rest of this chapter, we are going to be going over how to determine when series converge or diverge. And I'm going to remind you again, we often don't know what a series converges to if it does converge. In this video, we're going to be going over the first of many series convergence and divergence tests. It's exciting. Let's go. So this is known as the nth term divergence test. It tests only to see if something diverges. But we're going to start out with a really basic idea first that sets the tone. Given that you have some series of a sequence, right? So sigma from n equals 1 to infinity of a sub n, given that that converges, then the limit as n goes to infinity of that sequence, it's gotta equal 0. It has to. And the reason why this makes sense comes from if you take this thing and you expand it out, you're gonna see that if we have n equals 1 to infinity, we'd have of a sub n that would be equal to a sub 1 plus a sub 2 plus a sub 3 plus and so on and so forth until we get to a sub n, and then we keep going after that. If the limit does not equal 0, what that means is we would be adding numbers that don't go to 0 again and again and again as we get out to like infinitely many terms, which means we're constantly changing the sum. So if this didn't equal 0, the series would never actually flatline or converge to a set value. So if a series converges, that nth term way out in infinity, 0, right? It's got to be 0. Has to be. Now, from there, we can then flip that around and do the, well, what's known as the, contrapositive, if you must be very fancy with logic, but we don't have to be. This says if the limit as n goes to infinity of that sequence a sub n does not equal 0, then what we would know is that that series that we had from the last page would diverge. So then that diverges. And again, that makes a lot of sense based on what we just talked about. I'll go back to this. If this term does not equal 0 as we go out to infinity, we're adding a number that is not 0 again and again, meaning we're changing the end value, there is no end, of this thing. It never stabilizes, and so we would diverge. That's known as the nth term test. So all we have to do then is take the limit as n goes to infinity of the sequence, right? The series generator, that listing agent, if you will, and if it doesn't equal 0, then we know that the series diverges. If it does equal 0, the test actually fails. We'll talk about that in a little bit. So when do I use this test? You're going to see me say this a lot in this chapter. When should I use this test? Because it's one thing to know how to use the test, but you also need to know when to use the test. Like diagnosing, when a doctor says, oh, we should use this medicine in this case. Well, you should use this series test when you believe that the limit does not equal 0. So if the limit of a sub n does not equal 0, or you think it might not, take the limit as n goes to infinity of this. It's a very quick test. Or when you have no clue what series test to use. So you look at it, you're like, I don't even know where to start. Start with this test to see if it works. All right, that's it. Let's keep going. Let's actually use the thing. So this says use the nth term divergence test to show each series diverges. And what we're going to do is I'm going to now introduce you to how to justify each series formally. Because if you're taking the BC exam, you're going to need to know how to do this. And some college professors in Calculus 2 and teachers as well in BC Calculus in high school will require you to be able to justify your answer. So we'll go through this list at the bottom here, but I'm going to show you in action first how to justify. So first things first, I'm looking at this and I'm thinking 3/2 to the n. If this goes to infinity, I don't think this will equal 0. And sure enough, it won't. So I'm going to start out by saying the limit as n goes to infinity of a sub n. In this case, that's the function 3/2 to the n. Well, what does that equal? Well, if you think about it, that equals 3/2 to the infinity. I mean, you can't really plug in infinity, which is equal to infinity. So that doesn't equal 0. This limit doesn't even exist, right? You could also say the limit does not exist. So what we would say to justify this formally is by the nth term divergence test, this series diverges. So I'm going to write that out. By nth term divergence test, you wouldn't abbreviate on a test, of course. Just saving you the awfulness of having to watch me write the whole thing. By the nth term divergence test, this series, so the series, diverges. And what you've seen me do now with this justification, you've got all three of the components that you need in any order. When you justify, real formally, you need three pieces. You have to state the name of the test you used. Here's the nth term divergence test. You have to demonstrate the test's conditions. In this case, the test's condition is finding the limit and showing that it does not equal to 0. And then you have to make the conclusion that the series either converges or diverges, which we did. You can do that in any order. You could have said, this series diverges by the nth term divergence test, and then show the justification of the algebra right here. Doesn't matter the order you do it in unless your teacher says otherwise. Now, looking at this one here, let's diagnose it. I look at that and think, well, that limit's pretty easy to take. Let's see if we can use the nth term divergence test for this one and see what we get. Well, the limit as n goes to infinity of, and now we're just going to take that limit of 5n squared minus 3n all over 6n squared plus 1. Now when we take the limit of that, remember, you're taking the limit as n goes to infinity, so only the highest power terms matter. So that's approximately the limit as n goes to infinity of 5n squared all over 6n squared. The n squareds divide out and you're left with 5 over 6, which does not equal 0. That part's important. You're showing the person who's grading your work that you understand that the limit is not 0. So again, I would state by the nth term divergence test, the series diverges. Now, I'm going to repeat as I said in the last page, and I'm going to go over this in the next page as well. If the limit of any of these series did not equal, well, did equal 0, I should say, we cannot say that the series converges. The nth term divergence test shows divergence. You need to get close to the camera on that one. It only shows divergence. If we get the limit equal to 0, the series could diverge or it could converge. What that means is it's not the correct test for the job. That's what that means. And I'm going to kind of go over that specifically here. So I say careful! If the limit as n goes to infinity of a sub n equals 0, then that series that we're testing the convergence or divergence of does not necessarily converge. For example, this one right here, the series of 1 over n, that's the harmonic series from n equals 1 to infinity, is equal to 1 plus 1/2 plus 1/3 plus 1/4, and so on and so forth. Now, when you take the limit as n goes to infinity of 1 over n of this thing, you do get 1 over infinity essentially, which goes to 0. That means that the nth term test fails. So nth term test fails. And you need to use another test. So if you're using this and you're like, I'm not sure what test to use here, let me start with the nth term test, and you get it equal to 0, then you go to your next level of tests, which we'll learn later in this chapter. Now, you'll realize that limits are a big part of this, so if you're having trouble with limits, look back in chapter 1. You will see tons of exercises in chapter 1 on how to evaluate limits as n goes to infinity. All right, this one right here, so even though this test fails, I just got to kind of point out, this ends up diverging. 1 over n does diverge. So I'll say later, you will see this series diverges. The harmonic series diverges. But we're going to need a different test for that. It involves an integral. It's very cool. Now this one right here, this actually ends up converging. This is 1 over 1 squared plus 1 over 2 squared plus 1 over 3 squared plus 1 over 4 squared plus dot 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 plus 1 over n squared, and it keeps on going. Now this one here, the limit as n goes to infinity of 1 over n squared also equals 0. It equals 0 as well. However, this series, it does converge. That's kind of interesting. So I'm going to write here again that the nth term test fails. So you can't use the nth term test on this one. At least we tried. Later, you will see this converges. And so all we need are just 2 examples, counterexamples, I guess. One where we still diverge even though it equals 0, and one where it converges where it equals 0, to show that the nth term divergence test is only used to show when the limit does not equal 0. If it equals 0, the test is inconclusive, it fails. All righty then. Well, that's all I've got for this one for you guys. In the next video, we're going to go over a new series type. It's going to be awesome. Until then, I hope you're awesome. Peace.